Okay. So today we will mainly discuss about the problems left for you on quotient spaces, and yeah, and we mainly focus on quotient spaces only in today's tutorial, and in next tutorial maybe I will bring some problems from homeomorphism, and then that regular, normal, and all those kind of spaces. So let's start today's session on quotient space. Okay. Let us briefly recall few things which we understand. So yeah, let x comma tau be a topological space and this be a decomposition or you can say partition of x into subsets. Okay, so now we let us take a subset D such that we take the union of this f belongs to this script f is open in X. Okay, and take this sigma be the collection of all such is script f, right? Then what will be that sigma? What is the standard name? Then this D comma sigma is called the quotient space, right? Okay, so at first I quickly verify that this sigma is actually topology. Yes? Any question? Okay. So can you now this sigma is a topology, right? So can you quickly give me the three arguments why it's topology? This and this is the empty set and
D.
script D belongs to sigma. This is obvious, right? Because if you take the union of elements, then this means this set, if this union, this will be your whole X, right? Because it's a partition. Number two, take I belongs to some index set, be an arbitrary collection. And then take the union of Fi. Yes. So you have to prove that this union I belongs to I, this Fi. This belongs to sigma. So why it is so? Because so to prove this one in sigma, say it is say the script S. So what do you have to prove? To prove the union of F belongs to this set, right? Union I belongs to this I, F I, right? But what is actually this set? How do you write? You can write this as union of, bring this index outside, I belongs to I, and then union of F belongs to this F, right? Right? Now this set is open by the assumption, because each of Fi an element of, say it is in an element of sigma, and therefore this is actually arbitrary union of elements of what? Arbitrary union of open sets in X, and therefore this set is open in X. That means this collection is open in X, and so we have union I belongs to I is Fi belongs to sigma. Right? Now the third one. This is the what? See, so far we did not use the term. Yeah, we have used the term that there is a partition here to prove that this could be in sigma. But now we need that argument. So to prove the finite intersection, right? So, but for the finite intersection, it is enough to take two elements. Now let this F1 and F2 belongs to sigma. You have to prove this F1 intersection F2 belongs to sigma. Right. So to prove this one, we say the set. Yes. There is some internet issue like this. Okay. So now you have to prove that this intersection is again in this collection sigma. So for to prove this one in sigma, so which collection you should which union you should take? Union of F belongs to where? Right. If you respond quickly, then I should then only I will complete this proportion quickly. Right? So you should tell something.
F1 intersection F2.
Yes, thanks, Kanishka. So this F1 intersection F2, right? So can we say from here that this set is open quickly? We need to break this set, right? Can we say that this set is open from this line only? No, right? Then so
Yes, sir. Yes, sir.
so then how do we break this set into two parts? We will break this one, union of A belongs to this F1 intersection union of F belongs to this F2, this one. Okay, now here to get from here to here, we need the concept of, we need that each F are actually equivalence classes. So how? See, one way is obvious, right? So because if you consider this one, then this is contained in that as well as that. So this is obvious. Now let's look at the reverse one. So we see this inclusion is obvious. right? Now, if we look at the reverse one, say some x belongs to this union, right? Union of this A belongs to F1 intersection union of F belongs to this F2. See, please understand this question very carefully, because whenever you use question spaces and question topologies, you have to handle this kind of equivalence classes always. Okay, and proving of this collection of topology is to give some idea about that only. Okay, otherwise this is very easy. There is nothing to prove. But I thought I should prove this one to give you some idea where we are using these equivalence classes and why these equivalence classes are important here. Okay. So now this x belongs to here means this implies x belongs to this one and this one also union of this belongs to F2, right? So what does it mean? X belongs to this union. Meaning this implies X belongs to some F1, where F1 belongs to this F1, and this implies X belongs to some F2, where F2 belongs to F2, right? You can have two element, one element from this collection where x belong x which contains x, and one element from this collection shift F2 which contains x as well. Now we will use the concept of equivalence relation, or the concept that this F1 and F2 are actually equivalent classes. Then from these two arguments, what can you say? See, if we see, can we always say this F1 equal to F2?
Yes, sir.
Why?
Yes, sir.
Why?
Because sir, it is
Equivalence classes
either
are
equal or either disjoint.
Yes, this equivalence classes, because F1 and F2 are equivalence classes with the property that they have non-empty intersection, right? Mainly this x, right? So therefore what we can say, therefore F1 equal to F2. Now once we have F1 equal to F2, we have x belongs to this F1 intersection F2 mainly, means there is some element F, or let me write in this way, this x belongs to F1 which belongs to this script F1 intersection script F2, right? So therefore we can write what? This union, this set, let me write it again, union of this F belongs to this F1 intersection union of this F belongs to script F2, this contained in union of A belongs to this F1 intersection F2, right? Now what we have now is that we have this set as union of, sorry, intersection of two collections, right? But this is arbitrary union of open sets in X, right? Therefore this is open in X, and similarly this is open in X, and therefore this set is open in X. and so we can say that is F1. So we can say is F1 intersection F2. Oh, sorry, script F1 intersection script F2. This belongs to this sigma, and so is this comma sigma is a topology, or sigma forms the topological, or it's a topological space, right? Okay. Now let us see an example. Means how beauty this topology, this quotient topology is. So say we can form some spheres. Means from two-dimensional from a disk to spheres. Means we can get some interesting topology from some given spaces. Okay. So let's understand one such, or let's look at this example. Consider this D2. So what is D2? This is the two-dimensional unit disk, right? So x comma y such that x square plus y square equal to 1 of, sorry, less than equal to 1 of course a subset of R2. That is, we are taking this one. Okay, so this is this closed disk. Interiors are always there with the boundary. Right. Now let us define a collection this one. Let's define yes. Now this, let us give a partition here where we denote each partition element as x comma y. Okay, for x y belongs to D2, or say it is x in x. Right. So how we take x comma y is, see, this xy is actually an equivalence class. So an equivalence class is mainly a subset of x, right? It is a subset of x actually. So that's why we write it as a set notation. So this is x comma y. This contains a singleton set whenever is x square plus y square strictly less than 1. Means whenever we have some interior point, so let me give the axis as well. So these are the axes, so negative and negative. Okay, so this is our x-axis, this is y-axis. Okay, so actually whenever we have points in the interior, we will take this single set as an equivalence class. On the other hand, we also take all elements x1 comma y1 such that x1 square plus y1 square equal to 1 whenever x square plus y square equal to 1. Means when we take, means we are taking all points in the boundary. We are taking all points in the boundary in one partition or in one equivalence class. Okay, right? So that's when you can say this partition as, say, by using axiom of choice, you can give any name here. Say it is 0 comma 1, or it is simply 1 comma 0, and all those. Okay. Now give quotient topology. Now apply the arguments of quotient space here. Quotient space on this D means namely the sigma which we have defined. Okay, and here note that we are giving topology on this X as the topology induced from this R2 means the discrete means the metric topology. Okay. So then if we consider this d comma sigma, can we quickly say what it would be? This d comma d with respect to the topology sigma with respect to the quotient topology. This is which space it will give you. It will give you some nice space. So can you quickly say? Can you understand? Means, can you tell me which space it will be? Yes. This is, see, we have all the points in the interior as it is, and we are identifying the boundary points to a single one, to a single point. Means we have a space in B, all the interior points will be there, and we identify the boundary to a single point. Then which space it will be? This is actually homeomorphic to this S2. Okay. Yes. Okay. So now let me describe further. So how do we see that it's S2? See. So suppose now consider this set as D2. Okay. Now consider this set after giving a partition. Means I put this red line here to say that this boundary this red line is actually an element. Okay, element of D. Now, if you take a point from the interior, then its neighborhood will be. So, if you take a point here, then and take a neighborhood, say U, then what will be this set? This one. See, in this neighborhood, this will be collection of in this neighborhood U. The elements will be the form x comma y, right? And each x comma y, if you take the union of this set, this will be simply union, so the set U. But earlier it was as a subset of D as an equivalence class, but now it will occur as a subset of X. Right? So therefore, each point has a neighborhood of this form. Now look at this point, the boundary point. This boundary, there see, indeed there is no boundary, but look at this class, this one. So what will be an open set containing this set portion? It will be of the form this one, right? The outside, this portion, or let me write this one. So if we see this pictorially, so this one, and this one is the point we have identified, and taking this neighborhood means actually we are taking this neighborhood. Okay, these dotted lines are in the opposite side. So that's mean, so we can see that this is actually homeomorphic to S2, right? So is it clear? Yes.
Sir,
Yes.
sir, please define sigma explicitly for this example.
Oh, defining sigma explicitly. So what will be the open sets?
Yes, sir.
Yes. Okay. Let me try. Actually, it will not always possible defining, giving this sigma explicitly. Okay, maybe I will try. Now we say an open set U belongs to sigma. Okay, now let me give all basic open sets. Okay, see sigma is a topology, and this topology, and in this topology we must have a basis, right? Now let me give you a basis for that. Now, if you consider a point from the interior, look at the point in the interior. Okay, then if you take any point, then what will be its neighborhood? This one. Say it is U, right? And whatever, and you can find out a point, you can find out a neighborhood which does not intersect the boundary, right? So therefore, whenever X is of the form, whenever we have elements of the form, sorry, X comma Y, when X square plus Y square less than 1. Okay, now if you take an element xy, then its corresponding element in X will be X comma Y, right? In the disk, and in the disk, this has a particular neighborhood, right? Say it is U. Now just take say U star, the neighborhood of this one X comma Y in sigma as this U star will be this X comma Y such that this X comma Y. Okay, let me write it as X naught. Okay, to specify such fixed point X naught interior point in the interior whenever. So we take this X comma Y whenever XY belongs to U. Okay, so this kind of open sets will be there for the interior points. Now look at now. So we have taken. So we have open sets which contains all open sets for the points in the interior. Now look at the points in the boundary of the disk. Now in script D, in script D, they are actually same. So this is 0, 1, right? This class, and this is actually, so all the collection X, Y such that X square plus Y square equal to 1, right? Now we want a neighborhood of this point in D, right? Means we want some open set in sigma which contains this point. So now if U is open in sigma containing 0, 1, then by definition what? Then by definition this union of elements X comma Y belongs to U. This should be open in X, right? By definition. Now this one is actually a set. Now look at, now come to the picture. So here is our 0, 1. Let me take a different color. See, here is our 0, 1, right? Now we are taking here is our 0, 1. Now we are taking this collection, these classes, such that this should be open. This entire union should be open, and this union should contain this 0, 1. Means that whatever open set we will take, this open set should contain the class, means this circle, this boundary circle in the disk, right? Also, since this is an open set, on for this kind of sets, sorry, this kind of elements in the circle, this kind of open set should be there, containing each element, right? This kind of open sets, and that is why we took an open set whose union. That is why we took an open set U which contains this one. It will be of the form this type. Means its pre-inverse in the disk will be of the form this kind of. Okay, this outside portion. That's what I took. So, is it clear now?
Yes, sir.
So actually, and I also think Sir taught you the Mobius strip, right? He told something about Mobius strip. So now try to see exercise. Okay, so now give me the result quickly. So 0, 1 plus 0, 1, and here we identify which points. We identify actually 0, x to 1, 1 minus x, right? And it looks like in this way. So we have this one, we have this one. Okay, take a different color now. We identify this one, okay, and this one. So this is the Mobius. Okay. The interesting thing is that its boundary, if you consider the boundary is a circle. Can you see it? The boundary of this portion or this one is a circle. It's a two-dimensional thing, and its boundary is a circle. Though if you take the cylinder, see if you instead of taking this identification, if you take 0, x, if you simply identify with 1, x, then it will give you a cylinder of this form. There it will have two boundaries. One is this one, another one is this one. Okay, so Mobius strip, it is important that it has one. See, its boundary is circle. Okay, and later, if in the next semester you take some course on algebraic topology, you will see that this give you RP2. See, this is a complex where you have boundary circle. Also, on the other hand, you have a disk, right? The boundary of disk is also a cycle. Now, if you identify this disk with this disk, means if you say, if you consider this one as X a topological space, you consider this as a topological space Y. Now you take X union Y. Okay, give some topology there and take the identification as this circle with this circle. Then this is a well-known topological space, and it's very interesting, called the real projective space or RP2. Okay. Anyway, so leave it for the moment. Let's come to this exercise. See, actually, sir, in class, this one, sir, give you as an this is, sir, give you some sketch. Now read the statement that you have a topological space Y. You can define, you have topological space X, and any given space, any given set Y, you can define Y comma tau Y, right? Sorry, Y comma tau F, where F is a surjective function from X to Y, right? This is the topology induced by this surjective map, right? On the other hand, if you are given a simply a topological space X, then you can also give a partition D in with respect to this function f, means the D will be the collections of all f inverse of y. This y belongs to y. This, of course, this is a partition of x. And in this script D, you can give a topological structure, or you can give the quotient topology. Say this D with sigma. This is the quotient this is the quotient space of X, right? Where the elements looks like, partitions look like, or decompositions looks like f inverse y. On the other hand, this given a function f from x to y onto function, you can define the quotient topology as well. The quotient topology is defined on y, but here this quotient space is induced from this set x also, is induced from x. But this statement, this theorem gives you the arguments that if we define this kind of two spaces, then D comma sigma is homeomorphic to this y comma tau f. Whenever, so this D is not all partition, this for this particular partition, this f inverse of y, such that y belongs to, okay. Actually, I thought today I thought to describe this or discuss this proof briefly. Actually, in class I gave you the sketch of the proof only, and I thought it is not that much easy. And that's I thought I will give, but the arguments I have used to prove this one are the same. Sir given you in the class. You can try it by yourself. Okay. Now tell me, can you prove this one by the arguments given by sir? If you can prove, then I will move to the next problem. Otherwise, I will prove it. Tell me whether I need to prove this in now, in the typical system. Yes, I cannot hear it. Yes.
यस सर, करवा दो प्रूफ। सर ने जो हिंट दिया था उससे नहीं हुआ।
नहीं हुआ? क्यों नहीं हुआ? अच्छा ठीक है। ओके, आई शैल प्रूव इट। Okay, give me 1 minute. Let's see what is. Yes. Yes, I have given the idea. So why this result is important?
Hello, sir.
Yes.
Sir, I guess sir, F is onto map and is and homomorphism also, sir.
Yes.
Then it is from F is open map.
Yes.
And F is closed map. From there we can say.
Yes, it is onto and homeomorphism, and from here you can you also have to prove it one, right? So it is open map.
उसको ऐसे बोल सकते हैं कि मतलब it is strongest topology where function is continuous.
हाँ. Yes, हाँ. तुम प्रूफ किया हो? हाँ.
सर एग्जैक्टली प्रूफ तो नहीं किया, बस ट्राई किए।
अच्छा, ट्राई किए हो? ठीक है। मैं आपको इससे करता हूँ, देखो। एक्चुअली ये प्रूफ तो एग्जाम में उतना नहीं आते, लेकिन ये प्रूफ जानने का इम्पोर्टेंट इसलिए है क्योंकि वो सब्जेक्ट समझना है। इसके बाद means after this course you will take a course on functional analysis. There you will see that the use of these kind of things like topology, and then whatever things you did so far like real analysis and linear algebra. So those are based on this one, and functional analysis is very important for the people who take analysis or even in mathematics also. Okay, so topology, this basic course is also important, but without question topology, topology is nothing. That's right. Okay, so yes, any question? Oh, unknown. Okay. So we have two spaces, right? One is y comma tau f, and another one is the script d comma sigma, right? And we are trying to give a homeomorphism here. Now let's define h from y to the script d by h of y. Okay, let me write another thing. F from x to y. It's an onto map. Okay, it's an onto map. H y is equal to f inverse of y. Right. So this map is well defined, right? We need to check well definedness when we define a function on a class, but here each class is a single point, so there's nothing to worry about. Means you are defining a set on y which itself is well defined. Now two arguments are clear from itself, right? So one is h is a bijection. Is it clear? Can you prove this one? It's a bijection. In class I prove it. So shall I prove it? It's a bijection. Okay. So before that, let me write these two sets explicitly. This. Okay. Now this is a d. What is this d set? This is f inverse of y, where y belongs to y. Okay. And we define sigma to be the union of f inverse, sorry, not in this way. And open sets will be of the form. So if f open in this means that the collection f inverse of y belongs to this f union open in x, right? And on the other hand, tau f. So if u belongs to tau f means this f inverse of u is open in x, right? Now, so should I prove that this is a bijection? Or you can prove it because the bijection, the terms are given why it's bijection is clear. It is surjective. Surjective is clear from the definition because this d is actually f inverse y. Y belongs to y, and if you take any element from d, then it will get the form f inverse y. So h of y is actually f inverse y. Okay. So it's a surjective. And for injectivity, takes h of y1 equal to h of y2. Okay. So you have to prove y1 equal to what? So this implies f inverse of y1 equal to f inverse of y2. Right? Now, if we take an element from there, this is actually subsets of x. Subset of x, right? So x belongs to F inverse y1 equal to F inverse y2. So this will imply Fx equal to y1 and this Fx is again equal to y2 and therefore y1 equal to y2. So thus h of y1 equal to h of y2 implies y1 equal to y2. So h is bijection. Clear? Now the main thing. So h is continuous, right? H is continuous. Okay. So how h is continuous? To prove h is continuous, let U be open in D. We have to prove that H inverse, or to prove H inverse U is open in Y, tau. Right. So to prove H inverse U is open in here, what we have to prove? H inverse U belongs to, you have to prove it is in TF. What we have to prove? F inverse of H inverse of U is open in X. So, yes, that is to prove F inverse H inverse of U is open in X. So, this one we have to prove, right? So far I did not use any technical argument. Now come to that technical part which are given to you. Okay, let me use this one only. So we have x comma tau a topological space. We have a map F which give you another topological space on to map on from x onto y. So this is y comma tau F. We also have F map here to this d comma sigma, right? And this d, from where does this d come? This d comes from here. So this is h actually, basically, right? Now look at here. So the elements of d are, those are of the form f inverse of y, right? Y belongs to y, and what are these f inverse y are actually equivalence classes. Right? Actually, if you take this correction, this will give you a partition, this D, and each partition gives you an equivalence class or equivalence relation on X. So we can say that these are actually equivalence classes. Right? Now, so can you remember I have defined the quotient topology on last class by giving an argument. So here I have defined. So X, we had another class of partitions X star, we had a map P where P of X was this X, the class containing X, right? We had this one, and here also in the decomposition we are also giving the same. So actually I want to use this map P here. So this is my P, and what does P take? So here each element, these X are actually some F inverse of Y, right? And so P of X equal to F inverse of Y. This is the map when X belongs to F inverse of Y. In other words, that is Fx equal to Y. This one. So actually from X comma tau to D comma sigma, or from X to D, this is our quotient map. We are defining this E comma X is equal to F inverse Y, where Fx means X is an element of F inverse Y. So is it clear how does we define the map P? Actually in X star we had several equivalence classes and we have defined this P of X to the X to be that particular class which contains the element X, right? And similarly for this case, but since we have the collection X star as D, we are taking it as Px is equal to F inverse Y. This F inverse Y is actually this X. There is nothing to worry, and this F inverse Y is same as this X, and this X is obtained by this equivalence relation only, the same equivalence relation, right? Is it clear?
Yes, sir.
So now from here we can also one more thing by this. So now what are the open sets on sigma? Let's understand that also. I have defined already that how do we get the open sets here at the beginning of this session. Those are actually union of these. Those are actually open sets, right? Yes. Now a set V open, or what I have taken is U open in D, right? This U open in D. So what does it implies then? Union of F inverse of Y such that this F inverse of Y belongs to where? U, right?
Tau.
Tau by tau.
Sir. Okay. Sorry.
This belongs to where? This belongs to tau. This entire union belongs to tau. Right, this is just the definition. See, too many notations are here. Okay, so I am now using this. U opening D, what does it imply? Let's forget about this. Okay, U opening D, this implies union of F belongs to U is open in X, right? Open in X, this is by definition. But what are the F's? F is an equivalence class. But what are F? This F is actually F inverse of Y belongs to U. So this is actually your F, right? But what is this? This one, can we say this one is actually your P inverse U? Can you say this one? Look at the definition. So Px is equal to F inverse U. We are taking each F inverse U belongs to U. This F inverse U is an, now take a particular element from here, say F inverse of Y1. Okay, take a particular element. So this belongs to U, right? So what does it mean? It means Y belongs to Fu. No, forget about this one. So F inverse Y1 belongs to U, right? Right? So this means, but this is actually a set. This F inverse of Y1 is actually subset of X, right? And P is a surjective map from here to here, X to this collection D. So we can say that this is actually belongs to P inverse. So we can say that this F inverse of Y1 is actually some P of X, right? So this implies yes, right? So P of X. So now if we take P inverse of U, it will be the union of F inverse of U such that Yes, this is union of f inverse of y such that, or simply this f inverse of y belongs to U. Now come to here. Here we are sending an element x to here by fx. Right. Now we are sending h of fx to D, an element f inverse of fx. Right. F inverse of fx. Right. So suppose if it is, right, but f inverse of fx is actually an element from here, but f inverse of fx is a subset containing x. In x, right? So what we can say is that p of x is actually f inverse of fx, and therefore h compose of fx is equal to p of x. So h compose f is equal to p. Therefore, what you can say is in p inverse of u is actually, it will be f inverse h inverse u, right? But this is open by this argument, and this is open implies this is open, means f inverse of h inverse u is open. But that was our claim, right? So to prove this one is open, so we have proved that f inverse of this is open, therefore it is continuous. Clear?
Yes, sir.
Okay. Set open in X, so this is the different one. And almost in here. Okay. Now the reverse one. Now H inverse is open. To prove H inverse is open, it is easy. Sorry. H inverse is continuous. You have to prove, right? So H inverse is continuous means it is enough to prove that H is open. So what we will do? We take an open set. Say V belongs to tau f, right? So V belongs to tau f means matlab this f inverse of V is open in X, right? This f inverse V is open in X, right? Now look at HV. HV is equal to, this is H of Y, right? Such that Y belongs to V. This is by definition of range. This is same as f inverse of Y such that Y belongs to V, right? So this is a subset of actually D, right? So now this is a subset of D. You have to prove that this set is open, right? So suppose it is, let me write it as this script f. Okay. Space is let me write it here. So, right. Now you have to prove that a set B is in D is open. So to prove this one is open, what you have to prove? You have to take the union of this f inverse of Y belongs to this f, right? This one I have considered as this is open to prove, right? But what is this set? This is actually this one F inverse of y, and this is what is this is actually F inverse of V, I can say. Let me I can give you a clear argument. There's nothing to worry. Okay, now what is H of V? H of V is H of Y such that Y belongs to V. This is F inverse of Y such that Y belongs to V. Right? This is, you have to prove this one is open. This is actually right. To put this one now, union of F inverse of Y, this one. So this is actually now a set. We have collection, this collection, these are collection. Now if we take the union of all this, Y belongs to V, what it will be? It will be nothing but elements. So Z, what does it mean? Z belongs to, this implies Z belongs to some F inverse of Y1, right? This implies Fz equal to Y1. But this Y1 belongs to V. So Z belongs to F inverse of V. Therefore, we can say this is actually F inverse of V. We have started F as a, so we have H of V. These two are same, but F is a continuous map. Right, and so this set is open in X. Hence, H is open. Clear?
Yes, sir.
1 minute. Union of F inverse Y element Z belongs to A belongs to star. This is a subset of F inverse V. Take this. Okay. So two more problems are there. One is this one. Actually, in last tutorial, I gave you this problem, but was not able to solve due to because of this time. So I think this after learning that much question space, I think you will be able to solve this one. Okay. So please solve this one now. Okay. And some of you told me that you should try and then tell me if it's not possible. So if you are not able to solve, so have you tried it? That problem. So this problem was that. So let me give you quickly explain the problem. So this one actually this is our R2, right? We are taking a subset of R2 which consists of all these points, including this line. So black, this line, and this portion. So this portion. Okay. And we are taking the projection of this one on x-axis. You have to prove that this map is quotient map, but neither open nor closed. the same problem, the same similar kind of problems I had discussed in the last tutorial session, and this problem was left for you as an exercise. Okay, but I thought I will solve this one in today's session, but not able to. So don't know. But I want to solve this third one. So again, I leave it for you. Just try to solve this one. Okay. So if it is not able to, if you are not able to solve, then please ping me on MS Team by maybe some of you. Then I'll solve it on paper and send it to you. Okay. I do not want to take time on this tutorial session. I'll write solution and send it to you. So if you want, so if you are not able to, so if you want to, if you are able to solve, then it's fine. But if you are not, then please ping me. I will send you the solution. Okay, handwritten solution. Okay, so now this one. So quotient space for T2 space need not be T2. What is T2 space?
Out of.
Yes, house stuff, right?
For all x not equal to y, there is just two open set x belongs to u and y belongs to v, so that the intersection v is empty.
Yes, ux, uy open set belongs to tau such that x belongs to ux, very good, ux, y belongs to uy. Okay, so though you are saying that ux and uy, but it is better, always better to mention that x belongs to ux, y belongs to uy. Okay, actually we are giving index here, and this it is I don't know, but it's always better to write this, and ux intersection uy is equal to empty. Now quotient space, the T2 space. Now consider x as r cross 0, 1. Okay. What is the space? We have this one R2. We are taking on R2. We are taking this line and this line. Okay. These two lines. Now we give a. What? We give. So what we need now? We need a partition, right? Partition or decomposition. So consider this D again of the form x class x bar such that x belongs to x. For x belongs to x, we define x bar. So this x bar, or say this x.
Hello, sir.
Yes.
सर ये 0,1 फाइनाइट सेट गिवन है या मतलब कलेक्शन ऑफ ऑल सर r क्रॉस 0,1 सर इट इज फाइनाइट सेट 0,1 गिवन है या मतलब लाइन के सारे पॉइंट
थर्ड ब्रैकेट है ना, थर्ड ब्रैकेट मतलब सेट, ये थर्ड ब्रैकेट है ना, दिस वन 0,1 थर्ड ब्रैकेट ना. In R, in R we are taking 0 and 1. This is subset of R. Two element set. This is not interval. For interval, the standard notation is either 0,1 of this notation, or of this notation, or of this notation, or of this notation. But I am using third bracket here. Okay, it's a set having two elements, 0 and 1. Clear? Yes. तुम कुछ और पूछ रहे थे क्या?
सर आपने मतलब r ड्रॉ किया, मतलब सेट ऑफ रियल नंबर एंड ऊपर वो लाइन खींची है ना सर, मुझे लगा y इक्वल टू 1 वाली लाइन है वो.
हाँ, ये तो y इक्वल 1 लाइन है, ये y इक्वल टू 1 ही है, वो y इक्वल टू 0 है, यही है, यही लिया हुआ है. ये x, हाँ, लेकिन इंटरवल नहीं है, मतलब जो बीच वाला पॉइंट है ना, ये नहीं है. ये नहीं है, बस ये जो रेड कलर की लाइन है, ये एंड दिस वन. Okay, so now we identify these 2 points. So where x bar will be x, 0 and x, 1 whenever x not equal to 0. Okay, let me write it explicitly. X bar comma x comma 0. Let me take the bar, or let me give you this one, x comma 0. This notation, okay, contains x comma 0. If it is your x and this is your x comma y 1, then we identify these two in a quotient. Means in the partition these two will be in the same set. But for x equal to 0, means 0 comma 0 will be the singleton set 0 comma 0, and 0 comma 1 will be your simply 0 comma 1 singleton set. Okay, see, for x not equal to 0, each classes is a 2-element set. But for x equal to 0 means for 0 comma 0 is a singleton set. Okay, this gives you a partition, right? This gives a partition, and give a partition or decomposition. Now give quotient topology. Quotient topology, or take the quotient space on D. On D. Okay. Then, so now see, this X is Hausdorff, right? This we are taking the subspace topology induced from R plus R. Okay. Then R plus R is Hausdorff, right? And therefore subspace of a Hausdorff space is Hausdorff. Therefore X is Hausdorff. So X is T2. Let me take different color. X is T2, right? Clear? Yes, no?
Yes, sir.
X is T2. Now, can you say whether D is T2 or not? With respect to quotient space or quotient topology induced by the standard map or induced by that natural map P, which gives you the quotient topology with, for that particular space or for that particular partition. See, we have in the, let's try to see. Oh, maybe base finish. Okay. Can you see my screen? Microsoft Whiteboard. I don't know how long it will take to start. Okay. Now look at this one. So then what will be the topology here? The topology will be, or the space will be, you have this, okay. So all those points will be here. This one, and with this point, and at this point. Okay. Notice that if you take any point here, then this point, those are still there, but this point is identified with that point, right? In the quotient topology. Now we claim that this D is not Hausdorff, or this can be written as this X with respect to this equivalent class. This is not Hausdorff. So why? If we consider this one, this class and this class, let U be a neighborhood, this belongs to U and this belongs to V, right? Now what will be a neighborhood of this one, 0, 1 in U in D? It will be of the form this, right? Such that its inverse image is open in X, right? So this this one, what will be its inverse image? This one union this one, right? Except this point. So this one, right? On the other hand, what will be this V1? See, let's draw the same picture again. No, we don't need same picture since we have various colors. This one. For this point, if you take this one, this is as a neighborhood, then this neighborhood will be its inverse image will be this one union this one and this one. So in any case, this U and V will have non-empty intersection. Is it clear?
So please repeat once again.
Yes, sure, I shall repeat. Let us try to understand the open sets of neighborhood of 0, 0. 0, 0 is here, right? In quotient space, any neighborhood, if you take say U, it will be of this form, right? This open set, this open interval.
Yes,
Look at this one. So what was we have identified all these points up to 0, 1 with all these points up to 0, 0 and except we leave this 0, 1 and 0, 0 and then identify all the right hand points to the corresponding these right hand points, right, at the base, at the bottom. So top, we have identified all the points in top and bottom except these 0, 0 and 0, 1. Now you see here, now we take the point 0, 0, then its neighborhood will be of this form. So we do not know what neighborhood. So if U is a neighborhood, then its inverse. If U is a neighborhood of 0, 0, matlab this union of this x comma 0 belongs to U is open in X. This is the definition, right? Definition of open set in the quotient topology, in the quotient space. Now what is this? So this one x comma 0 we are taking 0 comma 0. Then this one is this one is an open set in X containing 0 comma 0, right? So an open set in this is your R. This is your R. What will be an open set containing this one? This will be of this form, right? So this form intersection C. This is open set in R square intersection with X, right? Because of subspace topology. So it will be open set of the form this form, right? But here we have something more. We are taking this union. Means whenever we have an element x comma 0 for x not equal to 0, this element, so x comma 1 will also be there. This collection, if you consider it as V, if we have an element x comma 0 in V where x is non-zero, then x comma 1 will also be in V. Right? Clear? Because we are taking the union of all equivalence classes. Therefore, not only this kind of open sets, not only our open set containing this one contains see, an open set is not only contains this kind of intervals, it also contains it's actually this kind of intervals. For this kind of intervals, if we take the image, then this will give you an open set of x0, 0 in here. That's mean That is why I have taken for this red one, this is of this form, except this one containing 0, 0. Clear now? And similar thing holds for this point also. Right? Is it clear now? Yes? No? If it's not clear, I will explain again. No problem, don't worry. But please tell me if it is clear. If it is not.
Yes, sir, clear.
Tell me the true. Is it clear? Sure?
Yes, sir.
Okay, so what about others?
Sir?
Clear, sir.
Yes? Sita?
Sir, in this problem, only 0, 0 and 1, 0, 1 creating problem, right?
Yes, yes. Only 0, 0 and 0, 1 are creating problems. For the other points, if you take one point as 0, 0, and if you take other point from here, this is actually here. So you can get from the topology on R only, you can get separate neighborhoods, means disjoint neighborhoods. But for the point 0, 0 and 0, 1, we have the problem. That's why it's not hostile. Okay, so that is for the day. But please try to solve this problem. Okay, you may face this kind of problems in your exam. Also, maybe I will give you something to some map and ask you to verify whether it's a question topology or whether it's a question map or whether it is open or closed and all those. So that's all for the day. Let me stop recording and